related to the computational structure of impact assessment models. First, do you have some questions that's related to what I explained last time? Supply use framework, all clear, all good? Last year, in the past two editions of the course, I spent much time in the last lecture of the second module in digging some extra mathematical features related to the positivity conditions and so on. But I believe also thanks to the comments that I got from your colleagues last time, that maybe it's more beneficial to have some more calculation examples altogether. That's why I asked today to bring your laptop. Do you have your laptop with you? I encourage you in work in small groups. And from next week on, we are officially dividing you in the groups that you also will work also for the final project with. So now I encourage you not working alone, but working together, maybe more beneficial. And the idea is that we are trying to do together one exercise that is not so complex, but you will see that it starts becoming complex because it has a bunch of products and technologies and environmental transactions, and you will see that when the system to be analyzed is just composed by a few technologies and products, then it's so easy to manage and to handle calculations. But when things are becoming a little bit more complex, we are now analyzing something that has 6 products, 6 technologies. You will see that it's not so easy to grab the meaning behind your results. So it takes some time for you to set up the model and to especially understand and comment the meaning of the numbers that you are getting from the model. And this is so important because in the end, in the project work, I'm not assessing really the detail of the calculations and the quality of the numbers that you're getting from the modeling exercise, but I'm assessing your ability of digging into the number that you got and to justify properly justify the assumptions and way of calculating the OTF models and footprints, etc. So if you don't have any issue or question related to the theory part, I'm moving immediately. I'm just summarizing the most important concept. Whenever you are handling an input up and a supply and use model, first of all, it is not always necessary to deal with a system by modeling it based on a supply and use framework, because here we see that we are interested in specifically handling the cases where we have some byproducts. So that's why we go for a supply and use model. The supply and use model, so the way of collecting data into a supply and use table is the most general way of collecting transactions across technologies. So this is the starting point for any accounting table. But then, as you will see during the project work, out there you will find a lot of data that are already in the shape of a square input-output table. So technology by technology or product by product table, because these are more easy to be handled. Okay. The point is that these tables are actually some results of the elaboration of a more general supply and use table. So we applied some, or who produced such tables, applied some assumption on how to deal with the byproducts or multiple products. And we understood hopefully the meaning of such assumptions, so industry technology and product technology. We understood that we have a product supply and demand balance, so the total supply of products must be equal to the intermediate and final demand. But then we have 2 unknowns. We have the total product supply and the total activity by technology. So we defined last time 2 possible ways of handling this problem, and we noticed that we don't know anything about how the system is working in real life. So we just know that there are 2 possible ways of elaborating the make matrix in a way that it is representing 2 radically opposite different economic meanings. So we have on one hand the market share matrix, the small d, and then we have the small c, that is the product mix. So if we are writing balances that links product supply with technology activity, we approach two very different linear transformation that enables us to move from the technology activity to product supply. And these linear transformations are expressions of alternatively an industry-based or a product-based technology assumption. We made some examples, very simple example to understand the meaning. Then we got the final elaboration of the Leontief model. So we got the final Leontief production model based on the two alternative transformations. And then we realized that this equation is very, let's say, the structure of this equation is common. It's really the same, actually. The only thing that is changing is the matrix that allows to transform the use matrix from U to a, that is a product by technology matrix, to a product by product table. So U by D or U by the inverse of C. We realized also that it's not always possible to apply product-based technology. This for practical reason, because if there are some byproducts, then there should be within the system other technologies that are producing such byproduct as primary product, because there should be a substitution of such byproducts with other products, equivalent products produced by other technologies. And then we approach in the end to the final the end point, that is the calculation of the impact of the system that is operating. One way we can look at the one side of the coin by calculating the impact in terms of production-based accounting. So we are accounting for the technologies that are causing the overall direct impact of the system. We are simply multiplying the intervention, the environmental transactions coefficients by the total activity by technology with proper elaboration, depending on in order to match the row column shapes. While for the consumption-based accounting, there are some differences. Why? Because we need to directly invoke for the Leontief inverse matrix. So we have the Leontief inverse that is calculated based on a product technology, industry technology assumption, and then the other with the product technology. We notice that there are some differences in the way we are writing equations here. Because here we have a problem of allocation. So the consumption-based, remember, that is not just about to measure the impact, but it's something that implies also allocating the impact on multiple products. So this strongly depends on the assumption that we define for the product technology or industry technology assumption. I hope that these concepts are somehow clear for everybody. If not, please stop me. I'm trying to explain myself a bit better. Yeah, I updated the slides with some additional notes on the unit of measure. We tried to solve the example one, the one related to the heat and steel production, and I put these examples, all these examples in the Excel file. Then I left for you to play with the example 2, that is exactly the same in terms of dimension. What is changing, what makes the difference is that I added also some transactions in the use. And this is complicating a lot the interpretation of the results, because we have a very complex metabolism, even if we just 2 sectors, 2 products. But then it's not easy to comment and to have an idea about the final results in terms of impact. So it's really, really important that you start by playing with such very super simplified examples in order to understand how the model behaves. Then, very quickly, I told you that in order to unleash the capability of the supply and use framework, we can formulate a supply and use system of equation as a system of inequalities. So we can define the problem as a linear program, And this is really a matter of your creativity and the real result, the desired result of the impact assessment, because we can, to some extent, let's say, provide a soul to your bunch of equations, because we can define a kind of behavior by defining an objective function. We could define the objective function that we want, depending on the narrative about the scenarios that we want to model. And then we can add some constraints. So there may be some structural constraints. So we have some balances that need to be respected, like, for example, the energy balance. This is something very close, actually. So we have, in case the model is fully defined in energy quantities, we have demand-supply balance of energy quantities. So pretty much the same of, let's say, some constraints that are structurally binding the system in obeying to the laws of physics. Then we have the technology assumption. We can decide to go for one or the other, or even in more complicated cases, hybrid assumptions. We are now working with the hybrid assumption at the end of the lecture. And then we have some non-negativity constraints. And we can have some more constraints, because we may be in the need of having some more complicated modeling in our impact assessment, for example, by adding some policy constraints, adding some other constraints that may be useful in order to provide a more, let's say, a behavior of our system that is more in line with the physical reality. Is the idea. That's fine. And this is something that you can find again in the Excel file that I told you. In WIDIP. I reformulate the very same problem in economic units to sector to products into LP terms. So I redefine it as an optimization model. So you can check on the equations and understand how you can model in the very same way the same system. So we have the same system that could be modeled either as a system of linear equations or as a set of linear inequalities, so as an optimization model. And this way, the system is leading to the same results. So you have a supply and use system that is defining the very same system with the same set of constraints, let's say, leading to the same endogenous results. But I hope you got the point. With the optimization model, you can add further constraints in order to improve the modeling capabilities of this supply and use model. Then we jumped the Leontief dual problem for the supply and use framework. We jumped also the reduction of supply and use table to the equivalent input-output tables that are embedding the technology assumption. I just want you to be aware about the fact that anytime you find a technology by technology or product by product table, these are nothing but simply an elaboration of the root of such tables, that is a supply and use table. Okay, so these tables are embedding the assumption on technology. This is something you should be aware about. Okay, let's jump these. Okay, now let's try to deal with the example that I prepared for you. Again, this is a fictitious example. So this is a supply chain that is actually very oversimplified, let's say. But as you can see, it is not easy to collect all the data into a supply and use table. So now we are spending a bit of time in trying to understand how this reference production system is working and what it's representing. And then we are moving to the Excel, and we are trying to figure out how the information, so the technologies and products arranged here, are arranged into an accounting, a set of accounting tables, supply and use. What I hope you really understand from these guys is that you now have the knowledge about a general framework that may allow you to provide numerical models of whatsoever. So you need to model a chemical plant. Okay, I can arrange the data in the form of a supply and use table. I can provide fundamental balances, and I can define the model. And this is something that, to be honest, I found very difficult. during the last year of energy engineering, I am an energy engineer, and we spent a lot of time in digging into very complex thermodynamic studies. That is fine, fair enough. We spent a lot of time in studying technology. We spent time in studying how square gas turbine works, how coal plants, heat exchangers. That's fine. This is, of course, the most important thing, knowing about the technology. But then I realized that if someone is asking me how to provide and how to organize an Excel workbook in order to define a model of a system, it could be a generic system, I wasn't able to do this. So this, I think, is one of the most important takeaways of this course. Being able of defining one generic productive system composed by a number of technologies and products, define the boundaries well, organizing the data neatly into the form of a double keeping entry table, supply and use table, organize the data there, being able to account for the closure of the balances, mass balance, energy balance, monetary balance, and so on, and then also provide some models to perform some ex-ante predictions. So once we got the model, then we can make we can use Leontief production or price model in order to get some insights about what is happening if we are changing the boundary conditions. Then, of course, this is just the entry point. We have just the main structural constraints, the product supply demand balance, technology assumption, but then you must know that we could have any other equation we want in order to provide a better representation of reality. This, I believe, is the most valuable thing you can learn from this course, okay? To make a scale up towards more complex type of models. This could be very, very useful for your future career, I think, and I hope. So let's start with the dairy farm process. I uploaded in WebEx the updated version of these slides, where you can have all these slides and also the subsequent one with further details. Then we have an Excel that I uploaded again with the dairy farm. So it's just a set of Excel tabs that then we are looking together now. So the idea is that now we are looking, we spend 1 minute looking at this reference production system, then we are jumping to the next slide that is simply translating such reference production system into a set of tables, a supply and use system. So you see that we have a system that is composed by 1, 2, 3, 4, 5, 6 technologies. And then how many flows do we have here? We have electricity, heat, waste management, crops, milk, cheese. So we have 6 flows. 6 flows, 6 technologies. So we are arranging data in square tables, okay? So in principle, we won't have problems in applying either the industry-based or product-based technology assumption in this case, because we have square tables, square make, square use, that's fine. Then we notice something that is curious. We have some products that represent physical products, physical outputs like electricity. We have heat, we have crops, we have milk and cheese. But then we have also these that may sound strange. We have waste management. Waste management sounds more like a service. Like waste management is the output of waste incineration. We have waste incineration here that is consuming some electricity and is producing one output that is waste management. And waste management is something that is consumed by many different technologies. Of course, guys, here you see that this is like the provisioning of a service, but the real flow of waste, where is directed, how it's moving in the opposite direction, right? So we have a flow, all the flows of waste that are generated in the crop cultivation, dairy farm, or cheese factory are actually moving the other direction, right? Because usually you are producing waste that are processed by waste incineration.
I don't understand.
When you're running these technologies, like you have a crop cultivation, dairy farm, or cheese factory, you are producing some outputs, and then you may also generate some waste that you need to deal with this waste somehow. The idea in this reference production system is that such waste are collected by a process that is waste incineration that is incinerating such waste. But here in this case, we are seeing the waste incineration as some technology that is providing a service. Okay, so it's providing a service that is the incineration of waste, so waste management. I'm just commenting on a possible way of structuring a reference production system. You may also think to other ways of representing the same problem. You will deal with this in the project work. Because maybe you want to simulate a portion of reality that has also some ways of dealing with waste. For example, now I'm showing you one example on how we can deal with the waste management. We can define waste management as a product. As a product, it's consumed by other technologies, but the consumption of such product is actually representing a material flow that is moving in the other direction. Okay? So we see that we have products, technologies, we have some environmental transactions. We will see then later on which type of transaction are connected here. We have the power plant. Okay, how many technologies are producing more than one main output? So what are the multifunctional technologies here? Power plant that is producing heat and electricity, okay? And then we have dairy farm that is producing cheese and milk, okay? Dairy farm, the main output is supposed to be milk, of course, and is also producing cheese, but cheese is also produced as a primary product by the cheese factory, okay? This may happen. So we have the total cheese that is delivered as final demand. Now, given this reference production system, do you have some comments about the possible technology assumption that may better fit this system as a whole? Do you have some hints? Of course, if this is a real system, we are taking a snapshot of a system. We don't know anything about the system. Any assumption could be fine, okay? Because we don't know, we don't have real insights on how the system behaves. So now we can make some assumption. If the behavior of the system is this way, then I'm assuming one technology assumption or the other. So here I expect you to be able to comment something about the possible ways of dealing with these technology assumptions. In general, speaking about power plants, is the production line of heat and electricity fully separable, usually? No. So ideally, the way we could define the best technology assumption for handling these technologies is product technology assumption. So anytime we are producing electricity, we are also producing heat. Then we know that actually CHP plants are working either with thermal follows or electricity follows, so with methods usually adopted for running the technology. But for the sake of simplicity now, we are sticking on product-based technology. Anytime electricity is produced, electricity is supposed to be the main product, then also heat is produced with fixed quantity. This may be a reasonable assumption. Then, do we have any other byproducts? Yes, we have the dairy farm. What would be the best assumption for you? Any idea? Yeah, it's supposed to be, here is could be defined as a byproduct.
I say that you cannot produce more milk. Milk is the main product. If you produce cheese, some of the milk, they are related together. There is a technology that produces cheese as a
separate product.
So as a product, and it's not dependent.
This is one interpretation that is possible. I may reply you that in reality, we can even, as a dairy farmer, we can, different with respect to the power production, we can be allowed also to make a little bit stock. So if someone is asking just for milk, it's not said that I have also to provide some cheese. It's maybe closer to the reality, the case where the dairy farm could separate the production lines. But again, this is one assumption. In the final exam, what we are used to do is to provide some hints in order for you to understand which is the best assumption to use. Okay, so don't get scared. But in reality, I would say 95% of the time, you don't have real insights about how the system operates. So first, you may try to calculate the results with both assumptions. And second, you could provide to justify a little bit better to try to rehearse on the possible ways of setting this assumption to get one result. In reality, people that are doing SCA and that are producing values about SCA or cheese are totally overlooking this kind of stuff, okay? So this actually we will see, even if we are doing some fictitious analysis with some fictitious numbers, but then you will see that the output in terms of footprint is changing significantly. Okay, so this is something that we should put appropriate attention on this kind of stuff. Okay, so pay attention that we have also that each technology here is consuming a set of products. So this is not really a very easy supply chain, because there are many products produced even with byproducts, and then we have a lot of products consumed by each technologies. Okay. Yeah.
For power plant and also for dairy farm, can we assume product-based technology focus for them, but also for dairy farm, or probably
okay, now so far you just know how to handle one single technology assumption at a time. So we are now applying both product technology and industry technology also to get the numerical differences and try to rehearse about the difference, the meaning of the numerical differences, okay, that we are getting. Then I will show you how to apply a hybrid technology assumption in the end, okay, because this is something that is very useful in case you have a system that is composed by many different clusters of sub-technologies, sub-cluster of technologies with different properties and different behaviors, okay? Okay, so there is one dairy farm data tab here that you can find in the Excel file. So you have this Excel file here. You see there are 3 tabs. There is one with simply the supply and use table. Then there are the second tab with the footprint calculation, and the last with the hybrid assumption and the application of the Leontief model with hybrid assumptions.
Can you check if there is this file in Google? Please.
Okay. Should be. Sorry guys. Le slide non ci sono? Just give me 1 second. Maybe I uploaded the wrong academic year. Hope not. Materiali, teaching material. I see here there is the diary. Supposed, okay, it's strongly written here, but it's supply and use framework, dairy farm. So the Excel file is there, and then I also uploaded the other foundation of input-output analysis. Let me share the screen. I'm checking now the PDF. Here's the PDF that is uploaded in the website. No, sorry. This is the wrong one. Is the yeah, you're right. There's no here the the modified PDF. I'm uploading it now. Sorry, lecture students, computation structure, supply and use framework. See, here is the corrected version with also, yeah, the diary file. I'm uploading now these to the website. Save. Okay, you should find it, but the Excel is already there. Great. So let's now, and I'm giving you some minutes in order to look at the numbers here, and try to see if the numbers are correctly matching the reference production system, and to calculate the main accounting identities. So I ask you to open the Excel. Maybe if you want, you can work in small groups. As I said, the first thing is to have a look on the supply and use table and to first check if this is making sense compared to what we have seen in the reference production system, and then to calculate the total product supply, the total technology activity, and the transpose of the raw sum of the main table in order to see if the table is balanced. I'm giving you some minutes. Notice that there are two environmental extensions here. So we have the air emissions, not yet specified, and then we have water use. And notice that the type of environmental extension is unevenly distributed across the sectors. So these imply that the footprints may be very different compared with respect to the type of indicator that we are analyzing. And this is something that is always, again, overlooked. We are used to speak about impact like in a monodimensional way. There is the CO2, for example. But the impact is something that has a lot of gray scales and is multifaceted. Side note on the unit of measure, you see that there are three mass measures. So we have tons, tons, and tons. Then we have euros, thousands of euros. And then we have megawatt hours for electricity and heat. So you see that there are byproducts out of the power plant and on dairy farm that are quantified in the same unit of measure. So this is saying to me that there are no problems, in principle, in applying industry-based technology. There are no inconsistencies, because we have multiple products quantified in the same unit. Have you spotted the error? Is there an error? Let's see. Consumption of crops. So we have the crops here consumed by crop cultivation. And why is this supposed to be an error? Yeah, so the crop cultivation cannot consume its own output. Yeah.
In the scheme.
Okay, not in the scheme. So I should add an arrow like this, right? So I have the crop that I'm producing, and a part of the crop that I'm producing, I'm also taking for myself. Is that clear? So is this the way such numbers are arranged in the tables clear? And if you make up your mind in correspondence between the reference production system and the supply and use table? Yes? Any doubt? Just for making one example, starting from the demand, for example, you see here we have 43. This 43 here is represents as final demand in terms of milk, quantified in tons. Then we have the intermediate demand that is represented by the sum of all these rows, of this row. So we have 55%, and only the cheese factory is consuming milk. So we have the final demand that is demanding milk, and then we have the cheese factory that is consuming milk. Then let's have a look, and this is the demand side of the story. for the milk. Now let's have a look on the production side. We should look at this column here, product 2, that is milk. Again, quantified in tons, and we see that there is a column here that represents the technologies that are supplying milk as or either primary or secondary product. So we have here the dairy farm that is producing 98 tons of milk. And why we can say this is supposed to be the primary product? Because this, in terms of tons, is the major quantity of the output of the dairy farm. And the dairy farm, now let's take another color, and let's now this is in red is the perspective of the products. See, we have this line here that is the demand side. So we have an intermediate demand, we have a final demand, and then there is the other side that is the supply side. We have the technologies that are supplying milk. And let's now look at the other perspective, the perspective of the technology and not the products. Let's change the pen color, and let's have a look on the dairy farm. So we have the dairy farm here. This is the consumption of products for the dairy farm, consumed by the dairy farm. So we know that dairy farm, in the given snapshot of time, it could be one day, 1 year, the number that you want. Let's assume 1 month, for example. So we have the dairy farm in this column here that is consuming a set of commodities. So it's consuming crops in tons, it's consuming waste management service in thousands of euros, it's consuming electricity and heat in megawatt hour, and is also doing something more. It's generating some environmental pressure. So we have this last part here, the environmental transaction that collects either the air emissions and the water used. Okay? Can we sum all these values and provide a meaningful result? No. Why? Because unit of measures are not equal. We have a hybrid unit system here. What if the model is collecting transactions in euros? Then I can sum all the numbers in columns, and the meaning is the overall cost of production. And if I'm adding also the value added here as an additional environmental transaction, then I'm getting the total values of outlays. Remember the first lecture. Okay, let's now move to the other side. On one hand, we have the consumption of commodities by the technology, the dairy farm. Let's now look at the other side of the coin. Let's check the dairy farm here. We have the same technology, and here this row is representing the products that are produced either as primary or secondary product by the dairy farm, by the technology. Is the sum of this matrix, this row here, consistent? Yes, in this case. This is representing the total mass of output of the dairy farm in terms of either milk or cheese. Great. So I assume that is clear. Okay. Do you have some problems in understanding the difference between the reference production system and the supply and use table? If you are mastering these, then more than half of the course is done. Okay. You are able to distinguish and to translate a reference production system to a supply and use table and vice versa. Okay. Then let's have a look to the total quantities now. And the question is the total supply of, is the total demand of commodities equal to the total supply? So it's Q equal to itself. Did you check these in Excel? With vector, by manipulating vectors and not by using sum of something? Yes? Okay, so make this exercise by using matrix algebra. Yeah.
Why is the cell M21 dairy farm
M20? 21 water use here.
I have the scheme in front of me.
Yeah, let's check. Dairy farm, yeah, there's water use, supposed to be this vector here.
And it is a product.
Yeah, here, okay. This is supposed to I didn't put much attention on this point, but thank you for clarifying this. This is supposed to be an arrow on the other direction, also in this case. Depending on the type of flow that I'm consuming, I'm always taking numbers here as positive numbers, you see, 125, 66, 50, etc. But then, of course, these numbers, this value, may represent some quantities that are flowing in different directions. Okay. Also, in this case, in the case of the waste management, for example, waste management services are moving in one direction, but the corresponding material flow is moving in the others on the other side. So this is just a matter of conventions. Okay, but you're right. To be very precise, we should have put here another direction to the arrows. Okay. Okay, great. So have you calculated the total quantities here? Yes or no? Okay, so let's have a check. Reply to the question first. So is the table balanced or not? Is the table well defined and balanced? So we have 82 tons here, and then we have 82, and we have 98, 98, 37, 13, 31, 37. So this table is supposed to work fine. We have the equality between demand and supply. Then, if we have an economic table, we should also check if the total activity by commodity, sorry, the total activity by technology equals the total outlay of a technology. So this is the case. We have also economic units and a fully monetary input-output table or supply and use table. Okay. So we can move to the next step if the structure of the supply and use table is clear. And now we have one request. Yeah. 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 Curly brackets, one semicolon, one semicolon, one semicolon. Yeah. It's not working. Let me check how I solve these. I did this calculation here. So I have the product of matrix U times curly brackets 1, semicolon 1, semicolon 1, plus final demand. 6 and 1, just 6, 1. I don't know, but it's not supposed to work because it's just collecting the single element of the vector of matrix. So if you're putting 6, 1, it's like saying that you have a vector of two values, 6 and 1. Okay? How Excel, let's say, can know what you should put inside the vector? No, because you see here, otherwise it would be a 6-dimensional vector or matrix or I don't know, tensor or something like this. It is not working in Excel. Okay. Okay, guys, if you are fine with this, except for some small dots, I would move to the second part. So let's have a look at the question now, because now the problem is it's becoming a little bit more complicated. Of course, is the core of the problem is asking us to calculate the footprints of all the products of the system by relying on both industry-based and product-based technology assumptions. And then we have some, here's the results. And then I provide you some empty masks in the Excel tab in order to guide you through the calculation. Then there are some questions. What are the most significant numerical differences among products' footprints? You're supposed to look at the numbers and get numerical differences and identifying the hotspots. Then, are you able to explain the reason behind such differences? So you have to rehearse on the meaning of industry-based and product-based technology assumption, and then what technology assumption better fit the model technology. So we have already started this conversation on the point, and you will notice that if I were an environmental footprint analyst, I could manipulate a lot these results because I can play with numbers and technology assumption to let the people believe that my product has a footprint that in reality may be very different from, let's say, from the number that I calculated. So there is an uncertainty, and that these calculations are always carrying, that we should be very, very, very careful about. So let's try to. I provided you the empty Excel. Here, okay. The second tab, the farm footprint. You see that. Let me make a zoom out. You see here that you have the empty spaces to be filled. I provide you a guidance for doing so. That in the exam you are starting from the blank file. You're supposed to work with Excel in order to build by your own the model. So first, before start putting your hands on the keyboard, let's focus on the approach to be followed. You are starting from a supply and use table that works fine, is well defined. You understood very well. Makes sense. So we are starting from absolute values. The first step consists in calculating coefficients. We need to characterize the behavior of our technologies. So what are we doing? We are start by calculating the use coefficients table. You see, product by technology. And this is very simple calculation. Then we are calculating the market share matrix, the D, and then the product mix matrix, the C. Then, make the subsequent calculation easier, you can even think of calculating directly also the inverse of C. Notice that while D has the shape of technology by products, you see technology by products, and C is product by technology, the inverse of C has the same dimension of D, that is technology by product. Then I ask you to start by calculating this, not forget about the environmental transaction coefficients here. So let's calculate these gray blocks first, and let's try to look at the numbers and try to get the meaning of these numbers before moving on, okay? Have you already calculated this? Okay, so you can start. 5 minutes should be enough. Tomorrow the exam will be very, very more difficult than this, okay? You will work with Lorenzo on waste management, etc. You are also relying on optimization models. So try to gain the necessary skills now. You should get something like this. More or less. Sorry? Yeah. And?
Get the same results.
Inverse of the diagonal of x. Let's calculate it. Where's x? X is here, right? So it's a 6 by 6. Inverse of this times m unit 6. Yeah, it's 0 because it's a non-zero actually, because it's if you are adding the numbers here, it's 1 over the number. You see, it's 1 over 82, 1 over 80, 105, 1 over. It's simply the yeah. So how you can check if your results are fine? You cannot do much on the use table, or better, you can check if the calculation of the U and R are fine, just in case you have economic values. Why? Because you can sum all the numbers, all the technical coefficients and environmental transactions, so the value added, and you are supposed to get 1 total outputs. But in this case, you cannot do really much, so you have to hope that you hit correctly the keyboard. But for the C and the D, you can do something, because you can check what? The column sums. So you know that for the product technology, so for the product mix, the activity of the dairy farm is producing is 1 and is split over the production of 2 products that are, in this case, cheese and milk. So if you are summing all the columns, you should get here a vector of 1s. And the same here, because you have a market share of cheese that is 100%, that is split over the 2 technologies, in this case, dairy farm and the cheese factory. Okay? How many of you have completed the calculation of these items here? Okay, okay. Okay, so it's time to make question if you're not getting.
No, when I have to comment this, I understand. When I have to calculate, I did it, but I don't understand the position that.
Okay. Okay. So
I understood your comment. I can be way, but the if transpose I think that I will start by half. That's.
Yeah, you can. Okay, to have a better understanding about what the computer is doing, nobody is supposed to calculate this pen on paper. Okay, it's not useful. But what you can do is, if you have some dots, is to start from a 2 by 2 example. For example, you can take the 2 by 2 matrix. That is so easy. You can calculate the adjoint matrix, the determinant, etc. And you can do this calculation pen on paper. It would help much in getting a better understanding about how the model behaves. Then look at also the inverse of C. That is the same for the inverse of C. What's the meaning of the inverse of C? We have, whenever there is a demand of the technology activity, the technology activity is producing more than one, because this more is what is going to be saved as the byproduct of another technology. Okay, so you are, in this case, when you are invoking for the activity 1 by dairy farm is producing 1.07, and this minus 0.07 is a negative output of the cheese factory in terms of milk. Okay, so this is the meaning behind the inverse of C. But again, if you are summing all the columns, you are getting a set of ones.
Is it something meaningful that if I ask you one more milk from dairy farmer, he gives me more than one milk?
It's not more than one milk. It's providing you more than 1 unit of its activity. It means that it's providing 1 unit of milk. Sorry, in this case it's 1.07 unit of activity, implying that it's producing 1 unit of milk and then a bunch of cheese that is cheese that is no longer produced by the cheese factory. This is the point. Whenever you're speaking about these rows here, these rows you see are technologies. So you cannot speak about the output in terms of products. You speak as output in terms of technology activity. And 1 unit of technology activity of a technology that is producing more than one output means that you're producing more than one output. And then the secondary output is saved from the production of other processes that produce such output as the primary. Okay.
The elements of the C matrix and inverse of C.
Yeah. Actually, okay, these are of course embedding the same information. But operationally, you have here a matrix that is representing the share of products produced when the technology is increasing its activity. So if the activity of the dairy farm is increased by 1 unit, 0.93 is produced as a milk, 0.07 is produced as a cheese. This is exactly the same. If you are inverting this matrix, you are transposing the dimensions, and this is saying you that when the dairy farm is increasing its activity, it's not just producing milk, but it's also producing cheese. So you have 1.07, and this 0.7 is the cheese that have no longer to be produced by the cheese factory. So it's represented as a saving. This is the idea behind the negatives. These are saving of production by other technologies.
And yet the negative of the problem is if I ask a dairy farm to increase its activity by 1 unit, it's going to increase its activity by more than 1 unit.
Yeah, because in the end you're not asking to increase the activity, you are asking a product. The point is that when you are asking 1 unit of product in the equations, what is calling the model? The final demand. So if you are asking the final demand of milk, this matrix is saying to you that, okay, you are asking 1 unit of milk, but anytime the dairy farm is producing milk, it's actually producing something more than the milk. That is also the cheese, and this cheese would be negative with respect to other technology. That's the idea. So you are always remember that input-output models in general are demand pool models. So you start by defining the demand of products. This is how economic systems are working. They start from the demand of products. Are you getting these, guys? Can we move on? Because we don't have much time. I really want you to bring to the final stages of this problem. So we have now the R matrix also. I hope that is fine for everybody. Now we have just to apply to complex but not so much equations here, because we have to account for the footprints of products. Remember that footprints are defined by products, so it's not simply I put here for a reason these red blocks. I put these here below the products because while the the environmental transactions represent the environmental transaction per unit of activity by technology. Here the footprints are defined per unit of output of products, because these are property of products, not of the activity. So here I just have to write these equations that are quite elaborated from the point of view of the Excel. So we have R, E, industry technology, that is R by D, times the inverse of I, product by product, minus U, D, inverse. There's no final demand here. Then I have RE, product technology, and it's the very same equation, with the exception of the substitution of D with the inverse of C. Product by product minus U, inverse of C, inverse. If you apply these calculations, pay attention. In Excel, you start by declaring the operation as a function. Okay, so here you're supposed to do something like this: matrix multiplication of the first argument, then you have to add a nested matrix multiplication of the second argument by something that is the inverse of, in this case, is the inverse of something. So you have to declare the matrix inverse of I minus matrix multiplication of UD, and then you can start close the brackets. Okay, so it's not so easy, but you can manage it. Okay, if you find very difficult, simply split the calculation in multiple parts to begin. Yeah, of course, you can move the operators in the way you want. You can even start by saying matrix multiplication of matrix multiplication of matrix. Find the way that you find more comfortable. Okay? In the end, the point is that the results must be there, equal to this one. This.
If you write matrix M moles of RD as a first argument, and then M inverse of 1.
Well, it's the same.
Because I had just experienced today that it wasn't the same.
Okay. This is equal to write matrix multiplication of R, R by D, and this is the first argument, times M inverse of blah, blah, blah. And then you close brackets. Sure? Retry. I'm quite sure that the result is the same, because if you are multiplying R by D and then multiplying by the Leontief inverse, is exactly the same than multiply R by D times the Leontief inverse. Things are not changing.
There are some coefficients, the orange coefficients, that are really different.
Yeah. Yeah, coefficients are so different. Now, keep in mind that this is a fictitious example, so numbers are there just to make sense without really physical root, okay? But in reality, this is something that analysts must put a lot of attention on, because the results could be severely affected by the assumption. And tomorrow, you will see that depending on the technology assumption that you are doing, is not set and then the system will be feasible, that the model will react in a feasible way. You will see tomorrow that in case you want to model, for example, a system where you have a waste management that is consuming a stock of waste, that is producing the waste that is produced by a set of other products, of other technologies, sorry, then you have a balance of the waste that you should comply with. You cannot consume more waste than the waste that is produced. And if you're running the model based on industrial product technology, it makes really a lot of difference. You will see tomorrow. Okay, are you able to come here, guys? Have you calculated these coefficients? Yeah? Yes or no? How many of you approach these, complete this calculation well? Okay, I see some hands. Fine. So, how can you tell me about these numbers? Do you see something that is clear, something the differences are quite clear for you? I put below also a relative difference between the product technology and the industry technology. It means that if you look to negatives, it means that the product technology values are less than industry technology and vice versa. So let's say I would highlight some. First, let's focus on milk and cheese, because the problem was on milk and cheese that actually are the endpoints of our small supply chain. So we have that. What can we say about these numbers here? In general, product technology, the impact of product technology, so the impact calculated based on the second block here, are lower for the milk and greater for the cheese. Why the model behaves like this? Okay, I really want to bring you at the end of this exercise, so I left this kind of reasoning for you to work in group on this, okay? Because in the end it's not so difficult, it's just a matter of trying to solve the riddle and see what is going to happen if I'm using product technology or industry technology, what is going to happen to the system if I'm invoking for a demand of output. Try to rehearse on this by your own, then we are coming back to this if you want to have some insights. But I really want to bring you at the end of this exercise. We have just a few minutes now. Tomorrow, by the way, I'm not simply jumping one topic. I'm saying that you will also spend time tomorrow with Lorenzo in digging into these differences, okay? Fine, so let's now move to the second part of this, the last part of this exercise, that is asking us, after calculating the footprints, let's now solve the Leontiev primal model. So the footprints are like properties of the structure of our system. It's not even necessary to write some balances or primal or dual models for calculating footprints, okay? It's a property of our table, of our coefficients table. Now, last part, set and solve the Leontiev primal model, deriving total product demand, total technology activity, use matrix, make matrix, environmental transactions, either big R and RE, considering that crops, milk and cheese and waste management are produced according to industry technology. We discussed this previously. It makes sense to think that I can produce milk separately from the cheese. I have different machines for doing so. I can have some stocks in my company, so I can provide some mix without force my facility in building also, in providing also cheese, while considering power plant and boiler operating according to the product technology assumption. You know that electricity cannot be, and heat cannot be stored. So in this system, when I'm producing heat, I have a CHP. When I'm producing electricity with my CHP, it's likely that I'm producing also heat. So it's convenient for me to consider that there are two clusters of technologies and products that work with different assumptions. On one hand, we have the cluster that is composed by crop cultivation, dairy farm, cheese factory, waste incineration, that work with matrix D, so with market shares. So whenever a product is demanded, then it is produced by a share of different technologies according to fixed proportion. Like here, for example, we have cheese is produced 20% by the dairy farm, 80% by the cheese factory. Makes sense. While there is another cluster that works with the inverse of C. So we have the production of power plant that is also producing heat, that represents a saving of heat produced by boiler. Is the idea. Now, this implies that I have to consider the problem is all in the characterization of this matrix, this big V here. So, jumping back to the solution here, I I also provided you some, sorry, let me take this blank file. Here. Okay, so I also guide your solution here. So it's just a matter of filling the blocks with equations, and you will approach the final solution. So we have to calculate again the coefficients, and here is a matter of pointing to the previously calculated coefficients. Coefficients are not changing. They are a function of the technology activity. So they can be considered as fixed and equal to the previous case. We already calculated this. What is changing here is the make matrix, because we have the make matrix here that has two empty blocks. So we don't have any waste electricity and heat produced by, we don't have electricity and heat produced by the first technologies, and the other way around. We don't have crop, milk, cheese, and waste management produced by power plant and boiler. So we have two empty blocks. But then we can recognize that we can distinguish two clusters of technologies and products that work with different assumptions. And here is just a matter of identifying and characterizing this cluster working with the piece of matrix D that is identified by this set of product and technologies, and the other portion with the inverse of C. So you have just to pick the inverse of C previously calculated for this cluster and put it here, the D previously calculated for this cluster and put it here. Then you have a big V that can be used as a make coefficient table. Once you got this, then it's simply a matter of characterize U, characterize small r, characterize the coefficients, and pay attention in recalculating the footprints. These values will be different because we have minus UV. Because the coefficients V will be different. Now, you see here, the byproduct, the behavior of the system in producing multiple outputs is all inside here. If you are defining another matrix, V, small v, then also your footprints will change. Okay? So this is a way of defining better how the system behaves in order to improve the detail in calculating the footprints. Okay? And also in improving the way that the model is returning total values. So finally, it's just a matter of moving in the second part and calculating, applying the balances. So the Leontief production model, the technology assumption, here there is an hybrid technology assumption. You see that U and inverse of C are substituted with small v. And once these are calculated, then you can calculate all the other quantities. We can calculate big U, big R, big footprints, and also the make matrix. Just pay attention because the make matrix, this block here is calculated as D times the diagonal of Q, while this other block is C times the diagonal of X, all transposed. Because I expressed and I defined a cluster of technology as a function of product supply and a cluster of technology as a function of technology activity. Now, I know that time is not much, but I invite you and start calculating all these blocks by your own.
Why you just close the formula?
Yeah, it's the formula like this. Simply the link between the C and the X. And if you calculate these, you should approach to something like this. Okay? Let's start from the coefficients table. So, next one. U, V, R, RE. There's no need to take snapshots because I already uploaded these tabs in the Excel file, the previous Excel file, the one that I used for the supply and use framework. So these are the last tabs of the previous file. And these are solved.
All are the right side doesn't change.
No, because pay attention. The U coefficients and the R coefficients are both function of X diagonal inverse. Okay? We are defining coefficients depending on technology activity. Coefficients are always defined by technology activity, so they are not changing. What is changing is the way we are defining the make table, so the way the system behaves when multiple products are involved. Is the idea. Try to do this by your own. And there are some questions, guys. We have not time today to deal with all these questions, but the idea is that you should rehearse on the new values of footprints that we can calculate based on this hybrid main table, main coefficients table. We define a new way the system is behaving in providing products by products, and so also the footprints are changing. And these are supposed to be in the middle with respect to the previous fully industry or fully product-based technology assumption. So these are supposed to be more reflecting better the reality of the system that we are analyzing. Suppose that it's actually working like this, both industry and product technology. Then there is another question that is now, for the application of the model, considering 100 tons of milk as the final demand, and it is asked to rank the technologies with respect to their contribution to the total footprint. I give you five minutes to make up your mind and try to calculate the first items, then I'm commenting quickly the results.
Io quando cerco di fare nell'Excel, in Excel file, when I have to try to make the difference between E minus UV in the left side in the RE.
RE, sorry, left side.
4.9, 7.1 on the left RE is equal to
this one. Okay.
The difference in A minus U divided by B. The same calculation I have done in the previous Excel and it works, but when I try to use the B that we have changed with lots of zero,
zeros are the same. There may be troubles because if you are not fully compiling all the parts of the matrix, you may find some error like this. Because some portion of the table are not full of zero. If you are putting all items in all the cells of the matrix, then you will find. Okay. Have you calculated the coefficients, guys? Yes, no? Okay. Since time is running, I would just comment on the results that I got from the other questions, okay? So I have here some, just pay attention to the slides, guys, so we can end the lecture. So there are some questions here. So you see that first there is a comment on footprints compared to the previous values of the footprint. Of course, footprints will be different. Footprints will be different because we have changed the technology assumption. Then it is asked to consider a final demand that is different with respect to the baseline. In the baseline, so in the original supply and use table, we started from a final demand of milk and cheese with the given values. Now the problem is asking us to perform another analysis. So let's consider the same production system, but what if we are asking, instead of the mix of milk and cheese of the previous case, we are asking just 100 tons of milk as final demand. What is going to happen according to this technology assumption? And then the second question, rank the technologies with respect to their contribution to the total footprint of milk. So the point is that we can get some numbers with impact assessment, so we can get some footprints in the end, total footprints of 100 tons of milk. But we need to be able, in order to dig into such numbers, to provide some meaningful insights. For example, we can say, okay, now that I know that the footprint is 10 something, what I can do in order to improve the system, in order to make it better, to try to reduce the footprint. First, I have to be aware about the relative contribution of each technology in generating such impact. So one thing that I can do is in setting and solving the Leontief model here. So I have, as I said, the Leontief primal model, Q equal to the inverse of I minus blah, 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 blah times Y, and I'm getting the total demand of products. Then I have the total activity by technology. Of course, here I have to put exogenously a final demand. Let's put a final demand equal to 100 tons of milk as specified by the model, by the problem. And you see that now the behavior of the system, so the equations are solved. So we got the total supply of product, the total demand of products that are equal to the total supply, of course, that are necessary in order to deliver these 100 tons of milk to final consumer. Then we got the related activity by technology, according to the hybrid technology assumption that we did. And then we can calculate all the other values. So we can calculate the use table, so we can understand better what is going to happen when we are producing these 100 tons of milk as final demand. How much crops, milk, cheese, waste management, and system heat should be delivered to each process. The same for the V, the make matrix, and the same for the big R and the big RE. So we have the total footprints in terms of total air emissions and total water, total cubic meters of water consumed. And these are embedded into the unique final demand value, 100. But then we can realize immediately that we know the total value of RE, and we know also the emission by technology. So we can say, okay, we have a total footprint in terms of air emission of these 100 tons of milk, but how these are built up? What are the, let's say, the main source of this air emission in this system? So we can have a look on this. So we can have a look on the total part by technology and say that, okay, the best contribution, if we have to rank the system, the best contribution comes for, the highest contribution comes from the power plant, 285, followed immediately by the heat plant, boiler, 252, and then followed by the crop cultivation process, 119. And the last is waste incineration. So if we have this system here, and we need to improve the system, we have to rank the components and point to the component that is weakest, that is causing the major contribution. Okay. Things are going to be more complicated if we are producing more commodities as final demand, because we have multiple commodities, so the footprint is divided into multiple commodities also, and then we have the total transaction with the environment by each technology. There are many advanced techniques for decomposing the footprint of each product into the related direct emission by technology. So here, the point that I want you to understand is that there are then many other manipulation of the very same data that we have in order to get further insights on the number that we get. This is the end point of this lecture, okay? The end point is that if you have the data necessary to characterize a supply and use model, then you can perform impact assessment of whatever, and you can have also the instrument to get into this number and to decompose this number to get some insights. Great. So guys, I invite you and play with the model. By the way, sorry, there is also one very final question, but I invite you in trying to solve it by your own. You have a model now, so you can play by also doing some more advanced studies. For example, considering a maximum water endowment of 100 cubic meter, to which extent the demand of milk and cheese could be increased? Assume fixed share of milk and cheese produced. So if I'm increasing the production of milk and cheese, how much milk and cheese I can produce in order to hit the limit of 100 cubic meter? And you can start doing some more sophisticated analysis. This is just a matter of providing some linear programs. You have the data, you have the model, you can provide constraints, structural constraints and feasibility constraints and policy constraints, and check the endogenous result of this model that you have. This is a very powerful tool. Try to master it because it will hopefully will be very useful also for some next studies, maybe in other courses or maybe, who knows, in the future career. Tomorrow, guys, bring your laptop. I know that tomorrow there will be some turmoils in the station because there will be some strikes. So it's not easy, but I recommend you to do your best in order to come here in presence, because there will be Lorenzo that will try to do some very elaborated exercises. I recommend you to come here. See you on Monday.